Ohm's law is the cornerstone rule that tells us how voltage, V, current, I, and resistance, R, are related in a simple conductor. In everyday language it says, if you push more water through a pipe, increase voltage, more water will flow current as long as the pipe size, resistance, stays the same. Mathematically, the law is written as V equals I times R, where V is the voltage across the two ends of the component measured in volts. I is the current that flows through the component measured in amperes. R is the resistance, a measure of how hard it is for the current to pass measured in ohms. The equation can be rearranged to solve for any of the three variables. I equals V divided by R, current equals voltage divided by resistance, and R equals V divided by I, resistance equals voltage divided by current. A simple real-world analogy is a hill and a sled. The hill's steepness is the voltage, the sled's speed is the current, and the friction of the snow is the resistance. A steeper hill, higher V, makes the sled go faster, higher I, if the friction, R, does not change. The law works precisely only for materials that are ohmic, meaning their resistance stays constant over the range of voltage and current used. Most metal wires behave this way at ordinary temperatures. Power in an electric circuit tells us how fast energy is being used or produced. Starting from the definition of electrical power, P equals V times I watts. We can replace V or I using Ohm's law to get alternative forms that are often more convenient. Substitute I equals V over R into P equals V times I. P equals V times V over R equals V squared over R. This form is useful when you know the voltage across a resistor and its resistance. Substitute V equals I times R into P equals V times I. P equals I times R times I equals I squared times R. This form is handy when you know the current flowing through a resistor. These three equations are equivalent, they just highlight different known quantities. P equals VI both V and I known. P equals V squared over RV and R known. P equals I squared times RI and R known. Practical example, a 60-watt incandescent bulb is rated for 120 volts. Using P equals V squared over R, the resistance of the hot filament is R equals V squared over P equals 120 volts squared over 60 watts equals 240 ohms. If the same bulb were powered from a 12-volt source, the power would become P equals V squared over R equals 12 volts squared over 240 ohms equals 0.6 watts. Thus, the bulb would be very dim because power falls with the square of voltage. Analogously, think of a water turbine. Power is like the amount of water energy captured per second. You can calculate it by the pressure voltage times the flow rate current, or by knowing how much the pipe resists the flow resistance. Explanation: a resistor is called linear ohmic when its resistance value stays the same no matter how much voltage you apply. In a VI graph, a linear resistor draws a straight line that passes through the origin. The slope of this line is the resistance R equals V divided by I. When does a resistor become non-linear? Temperature rise. Most conductors increase their resistance when they get hotter. If the current is large enough to heat the material, the resistance changes while you are measuring, causing a curved VI characteristic. Material limits. Semiconductors, diodes, transistors, and electrolytic cells have resistance that varies dramatically with voltage because their charge carrier mechanisms change. Physical changes. Mechanical strain, magnetic fields, or aging can alter the geometry of the conductor, again changing R. Real-world analogies. Linear resistor, a clean straight pipe with constant diameter. Water flow current increases proportionally with pressure voltage. Non-linear resistor, a pipe that expands when water gets hot. The diameter effective resistance grows, so the relationship between pressure and flow no longer stays straight. Designers must keep resistors within a temperature range where R is essentially constant, or they must use components like metal film resistors that have a very small temperature coefficient. Mathematically, a linear resistor obeys V equals I times R, R constant. A non-linear device obeys a more complex function. For example, V equals a I plus BI cubed, example of a cubic nonlinearity. When doing circuit analysis, always check the datasheet for the temperature coefficient. and the power rating to decide whether you can treat the part as linear. Key takeaway: linear behavior equals constant R. Non-linear equals R varies with temperature, voltage, current, or other external factors. Explanation: resistors can be joined together to obtain a desired total resistance. The two most common ways are series and parallel connections. Series connection. The same current flows through each resistor because there is only one path. Voltages add up. Total resistance is the sum of the individual resistances. Rx series equals R1 plus R2 plus Rn. Analogy: walking through several doors in a hallway. Each door adds a little extra effort, resistance to your journey. Parallel connection. The voltage across each resistor is the same because their ends are connected together. Current split according to each resistor's value. The reciprocal of the total resistance equals the sum of the reciprocals of each branch. 1 over Rx parallel equals 1 over R1 plus 1 over R2 plus 1 over Rn. Or for two resistors, Rx equals R1 times R2 divided by the sum of R1 and R2. Analogy: several parallel lanes on a highway. The overall traffic flow current increases, but the speed limit voltage stays the same. Numerical example. Suppose we have three resistors. R1 equals 100 ohms, R2 equals 220 ohms, R3 equals 330 ohms. Step 1: series. R series equals 100 plus 220 plus 330 equals 650 ohms. Step 2: parallel. 1 over R parallel equals 1 over 100 plus 1 over 220 plus 1 over 330. 1 over R parallel equals 0.0100 plus 0.00455 plus 0.00303 equals 0.01758. R parallel equals 1 divided by 0.01758, approximately 56.9 ohms. Step 3: series parallel combination. First put R2 and R3 in parallel, then add R1 in series. R23 equals 220 times 330 divided by the sum of 220 and 330, which is 72,600 over 550, approximately 132 ohms. R total equals R1 plus R23, which is 100 plus 132 equals 232 ohms. Quick tip for exams: remember the sum of reciprocals rule for parallel and the simple sum rule for series. Write the formulas on the margin and substitute numbers step by step. Explanation: the temperature coefficient of resistance, often denoted by the Greek letter alpha, tells us how much a resistor's value changes for each degree Celsius or Kelvin change in temperature. The standard formula is R sub T equals R sub 0 times open bracket 1 plus alpha open bracket T minus T sub 0 close bracket, where R sub T is the resistance at the temperature of interest, T. R sub 0 is the resistance at a reference temperature, usually 20 degrees Celsius or 25 degrees Celsius, denoted as T sub 0. Alpha is the temperature coefficient expressed per degree Celsius. For most metals, alpha is positive, resistance rises with temperature. For some materials like carbon or certain alloys, alpha can be negative. Interpretation: if alpha equals 0.004 per degree Celsius, the resistance increases by 0.4% for every 1 degree Celsius rise. Real-world analogy: think of a rubber band that stretches when it gets warm. The original length is R sub 0, and each degree of heat adds a small extra length proportional to alpha. The total length at temperature T is the original plus the stretch. The equation is linear only over a limited temperature range where the material behaves predictably. Outside that range, higher order terms may be needed. Key point for engineers: knowing alpha allows you to predict how a sensor, a heating element, or a power resistor will behave when the circuit temperature changes, which is crucial for reliability and safety. Explanation: let's work through a typical temperature-dependent resistance problem. Problem statement: a copper wire has a resistance of 10 ohms at 20 degrees Celsius. The temperature coefficient for copper is alpha equals 0.00393 per degree Celsius. Find the resistance when the wire's temperature rises to 75 degrees Celsius. Solution steps: Step 1. Identify the given values. R sub 0 equals 10 ohms at T sub 0 equals 20 degrees Celsius. Alpha equals 0.00393 per degree Celsius. T equals 75 degrees Celsius. Step 2. Plug into the temperature coefficient formula. R sub T equals R sub 0 times open bracket 1 plus alpha times open bracket T minus T sub 0 close bracket close bracket. R sub 75 equals 10 times open bracket 1 plus 0.00393 times open bracket 75 minus 20 close bracket close bracket. Step 3. Compute the temperature difference. T minus T sub 0 equals 75 minus 20 equals 55 degrees Celsius. Step 4. Multiply by alpha. 0.00393 times 55 equals 0.21615. Step 5. Add 1. 1 plus 0.21615 equals 1.21615. Step 6. Multiply by R sub 0. R sub 75 equals 10 times 1.21615 equals 12.1615 ohms. Result: the wire's resistance at 75 degrees Celsius is approximately 12.2 ohms. Why this matters: in a circuit that supplies a constant voltage, the current will drop as the resistance climbs with temperature. Designers must therefore allow for this increase, especially in power handling components. Another quick example: negative alpha: a thermistor NTC type has R sub 0 equals 5 kilo ohms at 25 degrees Celsius, and alpha equals negative 0.0045 per degree Celsius. Find its resistance at 60 degrees Celsius. R sub 60 equals 5 kilo ohms times open bracket 1 minus 0.0045 times open bracket 60 minus 25 close bracket equals 5 kilo ohms times open bracket 1 minus 0.0045 times 35 close bracket equals 5 kilo ohms times open bracket 1 minus 0.1575 close bracket equals 5 kilo ohms times 0.8425, approximately 4.21 kilo ohms. Here the resistance decreases because the material's alpha is negative. Tip for exams: write the formula once. Underline open bracket T minus T sub 0 close bracket, and remember to convert the temperature difference to the same unit, degrees Celsius or Kelvin, as alpha. You measure the resistance of a metal resistor at two temperatures. At 20 degrees Celsius, the resistance is 120 ohms. At 70 degrees Celsius, the resistance is 138 ohms. Find the temperature coefficient alpha. Write the temperature coefficient equation for each measurement. R20 equals R0 bracket 1 plus alpha open parenthesis 20 minus T0 close bracket. R70 equals R0 bracket 1 plus alpha open parenthesis 70 minus T0 close bracket. Since both measurements refer to the same physical resistor, the reference temperature T0 can be taken as the first measurement point 20 degrees Celsius for convenience, making R0 equal to R20 equal to 120 ohms. Substitute known values into the second equation. 138 equals 120 bracket 1 plus alpha open parenthesis 70 minus 20 close bracket. Solve for the term in brackets. 138 divided by 120 equals 1 plus alpha times 50. 1.15 equals 1 plus 50 alpha. Isolate alpha. 50 alpha equals 0.15. Alpha equals 0.15 divided by 50 equals 0.0030 per degree Celsius. Express alpha in standard notation. Alpha equals 3.0 times 10 to the minus 3 per degree Celsius. How an examiner scores this. Correct identification of the formula 1 point, proper choice of reference temperature 0.5 points, accurate algebraic manipulation 1.5 points, final numerical value with correct units 1 point, total 4 points. Practical lab tips: use a 4-wire Kelvin measurement to eliminate lead resistance. Allow the resistor to reach thermal equilibrium at each temperature before reading. Record the temperature with a calibrated thermometer. Even a 0.5 degrees Celsius error can shift alpha noticeably. Bottom line, The temperature coefficient is simply the slope of the straight line that relates resistance to temperature on a graph. By measuring 2 points, you can calculate that slope directly. Explanation: below are several typical exam-style questions that blend Ohm's law with the temperature coefficient. Each question is followed by a short hint on how to approach it. 1. Basic Ohm's law plus power. Question: a heater rated at 150 watts is connected to a 120-volt supply. Calculate the resistance of the heating element and the current drawn. Hint: use P equals V squared divided by R to find R, then I equals V divided by R. 2. Series parallel with temperature effect. Question: two resistors are in parallel. R1 equals 100 ohms, metal, alpha equals 0.004 per degree Celsius, and R2 equals 150 ohms, carbon, alpha equals negative 0.001 per degree Celsius. The assembly is at 25 degrees Celsius and later warms to 75 degrees Celsius. Find the equivalent resistance at both temperatures. Hint: compute R1 at 75 and R2 at 75 using R sub t equals R sub 0 times open bracket 1 plus alpha delta t close bracket. Then combine with the parallel formula. 3. Find alpha from 3 measurements. Question: a sensor shows 2.00 kilo ohms at 0 degrees Celsius, 2.50 kilo ohms at 50 degrees Celsius, and 3.10 kilo ohms at 100 degrees Celsius. Assuming the linear model holds, determine alpha. Hint: use any 2 points in the alpha formula. Alpha equals open bracket R sub t minus R sub 0 close bracket divided by open bracket R sub 0 times open bracket t minus t sub 0 close bracket close bracket. 4. Temperature-dependent power rating. Question: a 10 ohm resistor rated for 0.5 watts at 20 degrees Celsius has alpha equals 0.002 per degree Celsius. If the resistor operates at 80 degrees Celsius, what is the maximum voltage that can be applied without exceeding its power rating? Hint: first find R at 80 degrees Celsius, then use P max equals V squared divided by R to solve for V. 5. Design problem. Question: you need an overall resistance of 250 ohms at 50 degrees Celsius. You have 2 identical metal film resistors each with R sub 0 equals 150 ohms at 20 degrees Celsius and alpha equals 0.003 per degree Celsius. Should they be placed in series or parallel to meet the requirement? Show calculations. Hint: compute each resistor's value at 50 degrees Celsius. Then evaluate series open bracket R1 plus R2 close bracket and parallel open bracket R1 times R2 divided by open bracket R1 plus R2 close bracket close bracket. 6. Mixed units challenge. Question: a thermistor has a resistance of 5 kilo ohms at 25 degrees Celsius and alpha equals negative 0.005 per degree Celsius. What voltage will develop across it when a 2 milliamp current passes through it at 60 degrees Celsius? Hint: find R at 60 degrees Celsius, then use V equals I times R. Quick exam strategy. Bullet: write down the core formulas first. 1. Ohm's law, V equals I times R. 2. Power, P equals V times I equals I squared times R equals V squared divided by R. 3. Temperature coefficient. R sub t equals R sub 0 times open bracket 1 plus alpha open bracket t minus t sub 0 close bracket close bracket. Bullet: identify knowns versus unknowns. Bullet: keep units consistent. Degrees Celsius for alpha, volts for V, amperes for I, ohms for. Bullet: check if the problem asks for a series or parallel combination before plugging numbers. Bullet: when multiple temperature points are given, treat the relationship as linear and solve for alpha directly. These questions test not only rote memorization, but also the ability to integrate concepts, a skill essential for any electrical engineering exam.